So welcome to this lecture. This is the part 2 of noise parameter lecture. So here I will discuss about equivalent noise temperature. So what is equivalent noise temperature? It is normally represented as TE, T suffix E. So we know that the thermal noise is we normally represent as Pn or N. Noise power is Pn or N, it is kTB. We know it is kTB. So K is the Boltzmann's constant, T is the temperature, B is the bandwidth in hertz. So what is noise equivalent temperature T? T is equal to N by Kb. So T is actually a hypothetical value. It cannot be measured directly. It is actually a hypothetical value. Okay. T is a convenient parameter often used rather than noise figure in low noise sophisticated UHF and VHF microwave satellite radio system. Okay. In UHF frequency, ultra high frequency, very high frequency, microwave systems, satellite system, in those kind of sophisticated systems, we use TE instead of noise figure. Okay, so TE is more convenient in those cases. So lower okay. So as noise equivalent temperature is less, that means better quality receiver. Actually, this noise equivalent temperature is also a parameter like a noise figure only. These parameters, these are the byproducts, we can call it. These are comes due to the noise in the system. So the noise affected system, there will be noise equivalent temperature. Okay, why? Because definitely these all things comes. Why? Because of that thermal noise only. Anyhow, as the temperature increases, definitely some noise will be there, and this noise causes some troubles to the circuit. This noise is added to the received signal and will get distracted. So definitely we need to avoid these kind of noises. So for more sophisticated systems, instead of noise figure, we consider noise equivalent temperature. So this describes the quality of the system. So as T is less means we have a good quality, better quality system. Noise figure of 1 dB corresponds to a noise equivalent temperature of 75 Kelvin. So noise figure of 1 dB is equivalent to noise equivalent temperature of 75 K. And noise equivalent temperature of an output receiver is represented as T is equal to T into F minus 1. We know that F is noise factor, T is the environmental temperature. Okay, T is the environmental temperature, F is the noise factor, and T is the equivalent noise temperature. So from this equation we can write noise factor F is equal to 1 plus T by T. So these equations are very important. They may ask problems related to this. Okay. So next is narrowband noise. So NC of T, narrowband noise. Noise normally we can represent it in a this is actually the frequency domain representation. Okay, so noise can be represented in frequency terms also. So NC of T is equal to N of T is equal to NC of T cos 2 pi f0 t plus ns of t sin 2 pi f0 t. NC of T cos 2 pi f0 t ns minus ns of t sin 2 pi f0 t. Noise is confined to a relatively narrow frequency band in the neighborhood of f0. So this is actually the narrow band noise representation. It is having a cos component and a sin component. That is, in phase component we call it as in phase and a quadrature component. Okay, so that means noise is actually affected in narrow band neighborhood of this f0. f0 is here, frequency here, so nearer to f0 the noise is affected. So it is a narrow band frequency. Narrow band representation of noise or in phase quadrature. This equation represents the narrow band representation of noise or in phase and quadrature component representation. So this noise normally we can represent it in two ways. This is NC of T, this is NS of T. Okay, so this is the resultant signal R of T. R of T can be represented as NC square of T plus NS square of T the whole raised to 1 by 2. That is, R of T is equal to root of NC square of T plus NS square of T. and theta of t is equal to tan inverse. Theta is the phase angle between the resultant and this component, NC of t component. Okay, so phi theta of t is equal to tan inverse ns of t by nc of t. So n of t normally represented as nc of t cos 2 pi f0 t minus ns of t sin 2 pi f0 t. So this is the representation of narrow band noise. That means noise is affected in frequency nearby f0. Okay, so this is the vector representation of that in-phase and quadrature components. Okay, this is the in-phase component, another one is the quadrature component. Sine wave plus narrow band noise is represented as, suppose consider a sine wave AC cos 2 pi fct, and we are adding, suppose we are adding a noise n of t to the system, to the signal. So x of t we can represent as AC cos 2 by fct plus n of t. That is, this is our sinusoidal signal or wave, input wave. N of t is the noise we are added into the system, into the wave through the system. Okay, so we assume that both the case frequencies are same. Okay, if the frequency is same, then only the noise will be get affected. No, so f is same. So A and Fc are constant. That means here AC or A is, this is the amplitude of the input signal, and Fc is the frequency of the input signal. Both are almost constant. There won't be any change in amplitude. Amplitude is fixed and frequency is also fixed. And here we are adding noise to the signal. So sine wave plus narrow band noise is represented like this. X of t is equal to AC cos 2 pi fct plus n of t. So you just study the expressions only, no need to study the derivation and analysis of these expressions. Okay, and that's about the complete analysis of noise.